Good day, grade 12 learners. Welcome to today's mathematics lesson. My name is Anelen Sindane. This lesson is brought to you by the Gauteng Department of Education in collaboration with Saibono Discovery Center. Our lesson for today is probability, and we are going to be concentrating more on our grade 10 and 11 concepts, and that will cover the definition of probability, the use of probability to solve problems. We are going to look at the terminology that is involved in probability, as well as use the tools that are used in probability to help us solve problems. That is our contingency tables, our tree diagrams, as well as Venn diagrams. And we know that the grade 10 and 11 probability contributes about 8 plus minus 3 marks. Probability in our exam, it's 15 plus minus 3 marks. So we should be able to get these marks. Our lesson objectives. By the end of the lesson, we should be able to define probability, use Venn diagrams as an aid to solve problems, use tree diagrams as an aid to solve probability problems. We should also be able to use our contingency tables to solve probability problems. We should be able to understand the concept of mutually exclusive events, independent events, complementary events, as well as exhaustive events. We should be able to use our probability identity, which is given as follows. It is also given in our formula page. And we should be able to use Venn diagrams that involve 3 events, and we should be able to solve problems that are there. For our independent events, we should be able to prove that events are independent using our equation that if the probability of A and B is equal to the product of the individual probabilities of A and B, then the 2 events are independent, and this should be exactly the same. Now we can refer to our CAPS document as well as our examination guidelines for 2021 on page 7. Our knowledge Venn diagrams, the definition of probability, outcomes, we should be knowing what outcomes are, our equations, we should be able to solve equations, and we should be able to use the product rule. Let us define probability. Probability is a measure of chance, likelihood of an event occurring, measured as a real number between 0 and 1. Now, if we have a probability of 0, it means the event cannot occur. If the probability is 1, it's certain that the event is going to occur. If we have a probability of 0.5, it means there is an even chance of an event occurring. So as we define probability, it is defined by the number of favorable outcomes over the number of our outcomes in our sample space. In short, our sample space is the list of all possible outcomes, and we said our probability should always be between 0 and 1. As a percentage, it should be between 0 and 100%, and we can leave our probability as a fraction or as a decimal. Now, our probability scale, we use this scale to answer questions that involve approximating, true-false statements where we say if the probability is 1, it is true. If the probability is 0, it means it cannot happen. But now we can use our probability scale to estimate chances of events occurring. For example, if I say, what is the chance that it will rain in Gauteng today? We cannot approximate to 0, but we estimate to unlikely. Looking at the day, it's sunny today, and we know that it rarely rains during this time in Gauteng, but we cannot rule out the possibility that it can actually rain. Hence, when we approximate to unlikely or likely, depending on the chances of that event occurring. We move on now. What is the probability of contracting the flu virus? We know very well that according to seasons, winter is a flu season and we normally have flu around this time. Hence, we would approximate to say it is likely because the influenza virus can attack at any time. The probability of winning lotto, that one, we have a 1 chance out of 13,983,816 chances. So you are able to see that it's unlikely. We can't approximate it to 0 because there are people who are actually winning lotto. Hence, there is a chance of it being won, but the chance is very small. Hence, we approximate to unlikely. Now, we have looked at the probability identity as well as the definition of our probability of an event occurring, where we say it is the probability of an event. We use the letter P for probability brackets. We use capital letters for our events in brackets. Number, small letter n, that is the number of times that event is going to occur over the number in our sample space. Remember, our sample space is a list of all possible outcomes. An outcome is a possibility in an experiment or in a particular event occurring. We have our probability identity given as the probability of A or B is given by the probability of A plus the probability of B minus the probability of A and B. The terms or and in probability are very important, and you will be able to see that once there is an and, it means there is an intersection. And normally when there is an and, we multiply, and when we have an or, in most cases, we are going to add our probabilities that we are going to get there. Moving along, this is illustrated using our Venn diagrams, where we are saying the probability of A is given on a different color and the probability of B is given on a different color. But where the two are having a common area, we call it an intersection because there's a possibility of the events overlapping there. We'll move on now to another concept, which is mutually exclusive events. Mutually exclusive events are events that cannot occur at the same time. For example, if I have numbers 1 up to 6 as an example, I know that I will have 1, 2, 3, 4, 5, 6. If, for example, I say set A, it's the event that the number is odd. So I will put the odd numbers in set A, 1, 2, 2 is not. So it will be 1, 3, 5. Event B is the chance that the number is even. That will give us 2, 4, and 6. So you are able to see that there is no number which can be even and odd at the same time. Hence, if you are having a set of numbers from 1 up to 6, you are able to see that the events of picking up an odd number and the chance of picking an even number, these are mutually exclusive events because they cannot occur at the same time. A number cannot be even and odd at the same time. But you will find out that on some events, it is possible to have sets that are overlapping, but for mutually exclusive events, our sets are not overlapping. And we say the probability of A and B is always given as 0 in our mutually exclusive events. And you will be able to see this on our probability identity, that the probability of A or B will then be given by the probability of A plus the probability of B. Because we are subtracting 0, we will not show that 0, and hence we will have our probability of A or B being given by the probability of A plus the probability of B for our mutually exclusive events. There is no intersection, hence we get our answer as such. We are going to use this concept when we are answering questions later on. Complementary events. These are events that are both mutually exclusive and exhaustive. So it means if A and B complementary, it means the probability of A and B is 0, meaning there is no intersection, and the probability of A or B will always give us 1. So the probability of A or B is given by the probability of A plus the probability of B. But because there is no intersection, it means that probability will be of independence, it will be given by 0. Hence, we will have 1 is equal to the probability of A plus the probability of B. So in order to get the probability of A or B, you are going to use the equation. You rearrange and make the probability of A the subject, like that. The probability of A will then become 1 minus the probability of B. And you will realize that this occurs in most cases. We know that if A and B are complementary, B will be the probability of not A. And we know that the probability of A plus the probability of B, in this case we substitute because the probability of B is the same as the probability of not A, which should give us 1. Therefore, if we are given the probability of not, we are able to find the probability of the other as given in the equations below. Using the diagram, you are able to see that anything that is outside the event A, we call it our not A, and it's shaded gray there. You are able to see that. Now, also, we should be able to see that different books use different notations, but according to the KEPS document, we are supposed to be using the terms not A. But I know that some books, to represent, if we are given the probability of A, the probability of not A is given as that A with a small apostrophe on top there. So it means you should be able to see that in some instances, this will be written by the probability of A plus the probability not A will be given as equal to 1, like that. That's another notation that we should know, but according to KEPS, we should be using the word not A, but because most of the literature that is available uses some of these notations, therefore we should be able to relate. Moving right along, I will just give an illustration using the same set of numbers from 1 to 6, which are normally used on our dice. You are able to see that to get event A, it's an even number, and event B becomes our odd number from the 6 dice outcomes. Therefore, we are able to see that these are complementary events because they cover the entire sample space. We will move along and look at independent events. For our independent events, the occurrence of one event has no influence on the occurrence of the next event. For example, if I roll a dice, the outcome from a dice, and then next I also toss a coin, the outcome on a dice will not affect the outcome that is coming from the toss of a coin because these are independent events. The occurrence of one event has no influence on the occurrence of the next event. That's independent events. Mostly for our independent events, we represent them on a tree diagram, and you will see as we move along. These are events that cannot occur simultaneously. Now, so we will see that for our independent events, the occurrence of event A has no influence on the occurrence of event B. Therefore, we use the probability of A and B is equal to the probability of A multiplied by the probability of B. Now, as an example, we are given that in a random physical experiment, A and B, these are two different events. It was found that the probability of A is 2 over 5. The probability of not B is what we are given. And the probability of A or B is equal to 5 over 7. These are the kind of questions that will require us to understand our concepts of complementary events, mutually exclusive events, independent events, as well as the use of our probability identity that I have mentioned before. This is done mostly in grade 10, but it continues and is examined in grade 12. Now, the first question that we should look at, we should calculate the probability of B. Now, remember I've mentioned that on our question, we want the probability of A or B, but what we are given is the probability of not B. So we need to work out the probability of B first before we can answer the question. I will do this as an example. Activities are coming at a later stage. You will agree with me that the probability of B plus the probability of not B should give us 1. Because these are complementary events, therefore the probability of B will be given by 1 minus the probability of not B. Using the equation 1 minus the probability of not B is 3 over 8, and this will give us an answer of 5 over 8. That is the probability of B. So we will get a mark for the method and a mark for the answer, and we get our 2 marks there. We move on to the next one. So the typed one looks like that. We will move to the second one. So it's the same question, but now we have to calculate the probability of A and B. Remember, we have talked about independent events, but the issue of independence is not mentioned on our statement. Therefore, we are supposed to use our probability identity to answer this one. And if you may recall, we should be using We have calculated on the previous question the probability of B, and we got it as 5/8. We should remember that our identity is always given by the probability of A or B is given by the probability of A plus the probability of B minus the probability of A and B. This is the equation that we are going to use to help us get the value of the probability of A and B. I will then substitute. The probability of A or B is 5/7. The probability of A is 2/5 plus the probability of B, we got it as 5/8 minus the probability of A and B. We make the probability of A and B the subject. We use our calculator. 2/5 plus 5/8 minus 5/7, and this will give us our answer as 87/280. As a decimal, this should give us 0.31. So 3 marks there for substituting into our probability identity correctly, as well as simplifying correctly to get our answer. Then we will get our 3 marks there. Moving along, we are supposed to answer the next question. It says, hence determine whether events A and B are mutually exclusive events, and you have to motivate your answer. Let's go back a little bit. We said for our mutually exclusive events, we know that for mutually exclusive events, there should be no intersection, meaning the probability of A and B must be equal to 0. But on our previous question, we did our calculation and we found the probability of A and B as 87/240. Let's quickly check that one. Sorry, it's 87/280. 280 like that. So now, are the events mutually exclusive? Let's quickly recall, what are the conditions for the events to be mutually exclusive? We said there should be no intersection, and we said the term and normally involves an intersection. So in this case, to answer, and you can see it's a hence question, meaning using your result from above, you should be able to answer this one. So our answer will be no. They are not mutually exclusive. The reason, because there is an intersection, or the probability of A and B is not equal to 0. Remember, the probability is given by 87/280. So because of that intersection, the events cannot be mutually exclusive. As our reason, which is our motivation, it's because the probability of A and B is not equal to 0. For events to be mutually exclusive, the probability of A and B must be equal to 0. We will move on to the next one, example 2. Again, you are having events A and B such that the probability of A is 0.5 and the probability of not B. This is how we get tricked in an exam if we do not read the information fully, is 0.3. The probability of A or B is given as 0.8. We are supposed to prove that A and B are independent events. So we have to determine whether they are independent or not, and we must use our calculations to do that. So our approach as well, we need to find the probability of B, which is given by 1, minus the probability of not B. So using our complementary events, so this will give us 1 minus 0,3, and this will give us our answer as 0,7. From here, we'll use our probability identity. The probability of A or B is given by the probability of A plus the probability of B minus the probability of A and B. So we will use the identity to find the probability of A and B. I will substitute the probability of A or B, 0,8 is equal to the probability of A is 0,5 plus the probability of B, it's 0,7, not 0,3. The probability of not B is 0,3. Let us be careful about that one. Minus the probability of A and B, which means I will have the probability of A and B rearranging. It will be 0,5 plus 0,7 minus 0,8. And this will give the probability of A and B to be equal to 0,4 using the identity. Now, what is the condition for the events to be independent? Let us now check what is the probability of A multiplied by the probability of B. I will substitute and get 0,5 times 0,7, and this will give us 0,35 as the probability of A times the probability of B. Now, remember we said for our independent events, the probability of A and B must be equal to the probability of A times the probability of B. So we are supposed to say whether the events A and B are independent. In this case, you are able to see that 0,4 is not equal to 0,35. Therefore, the events are not independent. Our justification, the probability of A and B is not equal to the probability of A multiplied by the probability of B. We will move along, and now look at our mutually exclusive events versus the independent events. So if two events are independent, they cannot be mutually exclusive. Independent events will always have an intersection, whereas mutually exclusive events do not have an intersection. The events are always disjoint. There's nothing in common. So to summarize the differences, we know that for our mutually exclusive events, the probability of A and B is 0. And from our probability equation, it is given the probability of A or B is given by the probability of A plus B. And remember, we are subtracting that 0 from our identity. Hence, it is only given by that equal. For our independent events, this should be mentioned in our statement that A and B are independent, or there should be a way of connecting the independence there. The probability of A times the probability of B will always give us the probability of AND. And in our probability identity, the probability of A and B can sometimes be substituted by the product of the probability of A and the probability of B. Now, let us look at ways of representing our probability outcomes. We said we can use our tree diagrams. We all know the tree diagrams. We also know our tables, which we call two-way tables, and we also know our Venn diagrams. If we have forgotten about them, I've used one, but we should be able to revise them quickly. Those who play that game called spinning, and in probability we call that one tossing a coin. Now, we know that if we toss a coin, theoretically the probability of getting a head becomes 1 out of 2 because the coin has 2 faces. Now, this other concept that we need to understand, there is theoretical probability as well as experimental probability. If I toss a fair coin 20 times, there is a less chance of me getting 50 heads and of getting 10 tails and 10 heads, because you will find using relative frequency, I'll be recording what I'm getting as my outcome, and that will give me the probability when I'm using experimental probability. When you roll a dice 20 times, you will not get the same number of outcomes if it is a fair dice, and in that case we use relative frequency to calculate our probability. But if we are tossing a fair coin, theoretically I have 2 outcomes, and out of the 2 outcomes it's a head and tails. If the chances of getting tails, it's 1 over 2, which gives me a probability of 0.5, and we shall look at a way of representing these outcomes. The first way is to use a table. First toss I can get head or tail. Second toss I can still get head and tail. For both tosses, if on my first toss I got a head and on my second toss I also get a head, my outcomes will be head and head, and I represent them on a table like that. I will have 4 outcomes. And how do I get the 4 outcomes? Because on each of the tosses my sample space is 2 head tails, and on the second toss my outcomes are still the same, head or tails, hence I'll have 4 possible outcomes. But the combinations also, I will have 4 of them. Now, questions will come where you are supposed to give whether you got 2 tails or 2 heads, then you just count how many of that outcome are you getting over the total number of all possible outcomes, which gives us our sample space. Now, we also use a tree diagram to represent our outcomes, where we are saying branches represent our outcomes. And we layer out our tree diagram in such a way that the first of the branches represent a particular outcome. If we are supposed to do the experiment or the trial 2-3 times, it means we should have 3 layers going to the right so that we are able to plot and represent all our possible outcomes. So the stem represents our experiment. For example, if it's tossing, rolling a dice, if it's picking from a bag, those are the kind of examples that we use in our tree diagram. Now, let us have that one. The first experiment that we did on the previous one, we tossed a coin, we represented outcomes on a table. Let's represent the outcomes on a tree. Same experiment. our outcomes are head or tails. So as we indicated, our branches represent our outcomes, and our outcomes are head or tails. The chance of obtaining a head is 0.5 and the chance of obtaining a tail is 0.5, as I have explained. Now, if we are to toss a coin twice, our outcomes will be represented as given there. It will be a head. If the first outcome is a head, the second outcome can still be a head or tails. Please note that you work with one branch at a time. Do not look at, so if my first outcome was a tail, my other outcome can be heads or it can be tails, like that. I cannot start having 3 branches now moving from one outcome if I know that my outcomes are always 2 head or tails depending on the experiment. So my outcomes will be given by head and a head, and you are able to actually use your probabilities because these events are independent. To get the probability of each outcome, you just multiply. So our outcome in terms of probabilities will be 0.5 times 0.5. 0.5, in this case they are the same, times 0.5, like that. For the next one as well, it will be the same. Let's move. Now, a bag contains 3 green balls and 4 white balls. 2 balls are taken from the bag at random, one after the other, replacing the first ball before the second one is drawn. Please let us read carefully, because here we can have our probabilities with replacement or without replacement. If we are having with replacement, our sample space will not change. But if there is no replacement, our sample space has to decrease. And we have to be careful when we are drawing our tree diagram and interpreting it. Now, let's quickly do the example. We are supposed to draw a tree diagram to represent all possible outcomes. Now, remember, we should start the number. So we'll use G for green. The number for the green balls is 3. The number for the white balls, we'll use W for white, it's 4. Remember, we can get the number in our sample space. We add all the balls in the bag, so it will be 7. Now, to draw our tree diagram, quickly we will have our outcome can be green or white. This is the first pick or draw. If the first outcome was green, the second one can still be green or it can be white. Check how I'm doing the branches. If the first one was white, I can still get a second one as green, or the second one can still be white. That's our second pick or draw. Our outcomes will be given by, we follow each branch, green and white, white and green, and then we will have white and white, like that. Those are our possible outcomes. Now, remember, sometimes we'll be expected to show our probabilities on our branches, and our outcomes should look something like that. So we have our tree diagram, first draw, second draw, our possible outcomes, and the probabilities of each outcome. Let's move along. Now, our question is, what is the probability that both are green? So, if both are green, we are looking at the probability that we have green and green. And from our diagram, our answer is there on our probabilities. We will take that one because these are independent events. It's 3 over 7 times 3 over 7, giving us 9 over 49. We are taking it from the tree diagram. Now, the first one is white and the second one is green. So we are looking at where we have the probability of having the first one white, the second one is green, and we will have this as 4. You take your outcome. There is your white outcome where you have white first and second being green. It becomes 4 over 7 times 3 over 7, giving us 12 over 49 like that. Number 2. Both are of the same color. Remember now, for same color, we want the probability of white, white, or it can be green, green. Looking at that, it means it can either be this or that. So we are going to add the two probabilities. The probability of having both white, it's 16 over 49, plus the probability of getting green and green, it's 9 over 49, and this will give us an answer of 25 over 49. Remember, I talked about the words or and and. Or we add and you multiply. Let's move on. Here is a tricky one. This one, I'll give you 3 minutes to solve it, and then we will mark it together and we move along. 3 minutes. Let us try this one. You come up with a tree diagram and you show all possible outcomes, including our probabilities. welcome. I hope you had an interesting engagement with this question. Let us quickly check if we were able to solve it. This is an exam type question and we need to read it carefully. Now, the probability that it will be sunny tomorrow is 1/3. If it is sunny, the probability that I will play soccer is 4/5. If it is not sunny, the probability that I will play soccer is 2/5. Determine the probability that I will does not play soccer. Now, we need more space. Let's quickly go back. Now, for us to find the probabilities, we must come up with a tree diagram to help us solve this one. So, how do we solve this one? We will draw our tree diagram. So, I will use S for sunny, NS for not sunny, I'll use for P for play soccer, and I'll use NP for not playing soccer. You are able to see that. So now, to start our tree diagram, we are saying we are looking at the weather conditions. It can either be sunny or not sunny. So if it's sunny, Abuile can play or he cannot play. If it is not sunny, he can still play or not play. Now, the probability that it is sunny, it's 1/3. I'll put the probability there. So it means these are complementary events. Either it is sunny or not sunny. So to get the probability of not sunny, we use complementary events. It becomes 1 minus 1/3, giving us 2/3. If it is sunny, the probability that he plays soccer is 4/5, which means if it is sunny, the probability that he does not play soccer becomes 1/5. We now move to the other branch. If it is not sunny, the probability that I will play soccer is 2/5, which means the probability that he does not play soccer becomes 3/5. So our outcomes will be 1/3. Sorry, it will be sunny, play soccer, sunny, not play, and we will also have not sunny and plays, not sunny and not play. Those are our 4 possible outcomes. But to get our probabilities now, remember we are multiplying, so it means it will be 1/3 times 4/5 to get the probability that it's sunny and he plays. To get the probability that it's sunny and he does not play, it becomes 1/3 times the probability of 1/5. This one, it's 2/3 multiplied by 2/5, and we also have 2/3 multiplied by 3/5. The question is, determine the probability that Abuile does not play soccer. So you are looking at where we are having NP, which is that one, as well as this one. So either it can be sunny and he does not play, or it cannot be sunny and he does not play. So to get our solution, the probability that he does not play will be given by the probability that it is sunny and not play, plus the probability that it is not sunny and he does not play, which will be given by the product. We are going to have 1 over 3 times 1 over 5, which will give us 1 over 15, plus 2 over 3 times 3 over 5, and that will give us 2 over 5. And when we use our calculators to add that, we'll get 1 over 15 plus 2 over 5, which would give us our answer as 7 over 15, like that. So that will be our answer for 4 marks. We'll move along. Now, there is also our contingency tables for our events. I know you have done this before. I want us to quickly determine the values of A up to E, and we should also calculate the probability that a person chosen at random from this sample of 300 people is female, is colorblind, or is female and colorblind. Let us quickly do that one. I will give you 6 minutes to answer A and B. 6 minutes. Let us quickly try to complete the table because we have already looked at this at our individual schools. 6 minutes. Welcome back. I hope you were able to complete the table to determine the values of A, B, C, D, and E. Now, we know that to get the value of A, it is easier. Our total there is 10. So to get the value of A, we'll say 10 minus 1, which will give us 9. 9 plus 1 will give us the total of 10. So we are sorted. A is equal to 9. To get our B, here we are having our totals going down. So to get our 100, which number must we add to 9 in order to give us 100? Our B will be equal to 100 minus 9, and that should give us 91. Now, to get the number of females, we already have one female and the total is 200. So to get the value of C, we are going to say 200 minus 1, and that should give us 199, like that. Now, in order for us to get the value of D, or let's start with E, E becomes, we are adding these going that way. It becomes 100 plus 200. This will give us 300, which is our sample space. To get the value of D, it becomes 300 minus 10, and that should give us 290, like that. So we'll get 1, 2, 3, 4, 5 marks for getting those. Calculate the probability that a person chosen at random from this sample space of 300 people is female. Now, we will use F for female, so the probability of being female. Now, how many females do we have? There are 200. So the number of females is 200, and our sample space is 300. That's how we'll get our answer. When we simplify, we get 2 over 3. The probability that a person is colorblind. Now, we have to find the probability. I'll use CB for colorblind. Now, we have our total for colorblind as 10 over, it's always over our sample space, which in this case is 300, and this will give us 1 over 30 as the probability of being colorblind. We want to find the probability that a person is female and colorblind. To get that probability, we will get the number of females that are colorblind. It's only 1 out of our sample space, which is 300. So our answer will be 1 over 300, like that. Let's move on to the next one. This requires us to use the concept of independence. Is color blindness independent of gender? We have to motivate our answer. And looking at this one and what we have done, we know that our A is 9, our B is 91, our C is 199, and our D is 290, and our E is 300, like that. We have done some bit of work on this. We said the probability of being female. We got our answer as 200 over 300 as an example, and that gave us 2 over 3. The probability of being colorblind, we got our answer is 10 over 300, which is the same as saying 1 over 30. The probability of being female and colorblind, we got our answer as 1 over 300. Now, we will use this to help us calculate and justify whether color blindness is linked is independent of gender or not. Let's look at, we have found the probability of being female and colorblind. We found it as 1/300. Now, let us check. What is the product of probability of being female multiplied by the probability of being colorblind? Let's see what it gives us. If it gives us an answer of 1/300, it means they are independent. But if it does not give us an answer of 300, it means colorblindness is dependent on gender. So the probability of being female, we said, is 2/3 multiplied by the probability of being colorblind, which is 1/30. This will give us an answer of 2/90, which is the same as saying 1/45. Now, remember, for events to be independent, the probability of being female and colorblind must be equal to the probability of being female multiplied by the probability of being colorblind. But when we look at this, these are not equal because 1/300 is not equal to 1/45. We know that. So it means the colorblindness and gender are dependent. So therefore, color blindness is not independent of gender, as you can see it there, né? So it means color blindness is dependent on gender. Even the results are showing of the 10 who are colorblind, 9 are males. So it means colorblind males are more colorblind than females. We'll move on now to the next activity where we look at Venn diagrams. Now, for our Venn diagrams, we know that we use a rectangle to represent our sample space, and we use circles to represent our events within the sample space. Now, we know that if we have that, we only have event A in the circle, and whatever is outside circle A, it means it's not A, but is within the sample space. For two events, we have discussed this. The two events are disjoint. There is no intersection, meaning whatever is not inside circle A is not A, and whatever is not inside circle B is not B, and it covers the whole sample space there. The events are disjoint. We move on now. We know how to represent this. The shaded regions are representing what we have. So in this case, we are looking at two events, and you are able to see our intersection. That one is for A or B. We can use our numbers or we can use probabilities for our Venn diagrams. And then you are saying A, not B. You are only looking at what is in circle in event A, but not in event B. The shaded region represents that. You are going to need this when you are answering questions or using our Venn diagrams. A or not B. So everything that is in event A is shaded, and everything that is outside event B is shaded there. So what is white? It's what we have as our B. Now, not A and B, and we are only looking at what is affecting or what is in event B in this case. Now, not A or B. Not A, you will shade everything outside circle A. Or B, you are shading everything that is affecting B. So you are only looking at only A. Not A and not B, or not A or B, you are able to see the shaded region represents that. And you are seeing that that one, it's not A and B, it's excluding our intersection, hence the shaded region there. Now, we also have Venn diagrams that involve three events, and you will see that the intersection of the three events will be given by the top one there. And we also have an intersection of only two of the events, which are A and C there. And then we also have the shaded region to represent the union. The union means A or B or C will be represented by the shaded region. And the last set of our Venn diagrams there represents A, B, and C that are disjoint. There is no intersection there. And our Venn diagrams can be drawn based on our outcomes in terms of our numbers or probabilities. When using our Venn diagrams, we always start with our intersection and we work our way out. We will see this as we move along. You complete the all first. If we have an intersection, this will actually apply mostly when we have three events. Start with the intersection of the three events and work your way out. Now, here is an example, but in the interest of time, I know you have already covered this. Sometimes you will be given a Venn diagram with information already given, or we will be given a question where you are supposed to fill in the information into our Venn diagram. Now, we've done something similar to this, but I would want us to quickly answer that question 7. I will give you 6 minutes to answer that question 7.1. 6 minutes. Welcome back. I hope you were able to apply what we have done. So you'll be able to see that for us to solve this problem, we need to calculate the probability of A and B. So you can see that in most of these questions, we need to use our probability identity. So the probability of A or B is given by the probability of A plus the probability of B minus the probability of A and B. So we are going to substitute 0.74 is equal to 0.3 plus 0.65 minus the probability of A and B. So the probability of A and B will be given as 0.21 after rearranging. So we have answered the first question, substitution into our identity, and for an answer of 0.21. The next question requires us to represent the information on a Venn diagram, and it's 4 marks. Remember, we said we are having, in this case, because we have calculated the probability of and there's an intersection, we have our A, we have our B. So remember, we said we start by filling in information on our intersection. So it's 0.21. So for this event A, we must have a probability of 0.3, meaning for our event A, only it's going to be 0.09. And for our event B, which is 0.65, we will have 0.65 minus 0.21, and that should give us 0.44. Our sample space is equal to 1 because we are working with probabilities. And we will get our probability, when you add 0.09, 0.21, and 0.44, you subtract them from 1, you will find the probability of not A or not B, which will give us the probability of 0.26. And we are going to get a mark for that one, a mark for this one, a mark for that. In the correct positions, we'll get our 4 marks there. The next question, are the events A and B mutually exclusive? You give a reason for your answer. In this case, mutually exclusive events, they should be disjoint. In this case, there's an intersection, so the events are not mutually exclusive. Now, we are going to look at the 3 events that we are having there, where we are having 240 customers buying burgers at an outlet on a particular day. So we are going to use the Venn diagram to help us answer the questions. May I give you 8 minutes to quickly answer this one, because all the information is given. We are just extracting the information from our Venn diagram. 3 events. Let's quickly do that one. I'll give you 8 minutes to answer the questions. Welcome back. I hope you were able to answer the questions. Now, remember, you are extracting information. All the information is already represented for us in a Venn diagram. So we will be able to extract what we need. The first question says, how many customers did not buy? So you want the number, not buy. Looking at our Venn diagram, how many people did not buy? We are getting our answer there. Our answer is 5. 5 customers or 5 people. You are done. 1 mark. Are the events B and C mutually exclusive? Remember, for mutually exclusive events, there is no intersection. But if you look at B and C, there is an intersection there. So the answer is no. Reason, there is an intersection. Because there is an intersection, they are not mutually exclusive. Or you can actually give the number in A and B is equal to 29 as your answer. We move on now to the next part. If the customers in this group is selected at random, determine the probability that he or she bought only a vegetarian burger. So you want the probability only V. How many people bought a vegetarian burger? You are extracting. Your answer becomes 58. It's a probability over our sample space, which is 240. Bought a cheeseburger and a bacon burger. A cheeseburger and a bacon burger. Are you able to see that one? The answer is already there. P, we want B and C. And that will give us the shaded region, which gives us 29 over 240. That becomes our answer. We move on to the next one. Let's move. We have answered those ones. We have answered 10.3.1. V only, we got our answer. We got our answer is 29 over 24. We are told, but did not buy a cheeseburger. Did not buy a cheeseburger. We are adding everything that is outside, including those 5. So everything that is outside, but not including the cheeseburger. So we'll get our answer as what? We are going to add everything that is outside, and we'll get our answer is 58 plus 3 plus 52 plus 5. Then we'll get our answer of not buying a cheeseburger. What a bacon burger or a vegetarian burger, we are going to add our numbers there. We will have our 58, this 58 plus 9, our bacon burger is still there, plus 12 plus 3 plus our vegetarian burger. We'll have our 52 there. We'll also have our 17 there. We add these, we should get 151 over 240. Or we just say, because these are supplementary events, we just say 1 minus the number that we are having there. Then we'll get 151 over 240. We exclude this one and that one, which will give us our answer there as that. You have seen how we approach questions for our probability. When you are supposed to get a number, you use the number. When we are supposed to get probability, we should always make sure that we are using It's over our sample space, the number in our sample space. We extract key information. We represent outcomes using appropriate diagrams, for example, our Venn diagrams, our tree diagrams, contingency tables, or we use whatever can help us get our solution. I hope this helped you. You will take a picture of this one. You will do it later on at home because time is not on our side, but these are the kind of questions that are examinable. And there is another one. You can take a picture of this one for homework, and you should be able to draw a Venn diagram to represent the information, and you are going to use your Venn diagram to help you answer 9.2 up to 9.4. We will move along, and we should get, there is another activity that can help you get a tree diagram there. Using that activity, you are able to see the way it's extracted. Then you answer the questions. Now we should be able, there is another activity that can help you prove whether the choice of a snack is dependent or independent of gender. You can take a photo of this one. Now we have come to the end of our lesson. I hope you learned something. So in summary, we learned the definition of probability as a measure of a chance or likelihood of an event occurring, and it's measured as a real number. It can be a decimal, a fraction, or a percentage between 0 and 1. As a percentage between 0 and 100%. We should also be able to recall that independent events, the occurrence of one event has no influence on the occurrence of the next event. And the formula for independence, the probability of A and B is equal to the product of the probability of A and the probability of B. Mutually exclusive events, we know that the occurrence, these are events that cannot occur at the same time, and we know that mutually exclusive events cannot be independent. We know our probability equation. The probability of A or B is given by the probability of A plus the probability of B minus the probability of A and B. We know that we use our Venn diagrams, tree diagrams, contingency tables as a way of representing probability outcomes and to help us solve the problems. And we know that probability should never be more than 1, or we cannot get a negative probability. Something would have gone wrong along the way. Let us practice, and we make sure we revise thoroughly our grade 10 and 11 probability so that we are able to get those marks that we need. Probability is very easy. Let us read and understand the scenario before we can answer the questions. Have a good afternoon. Thank you so much.